pleasure to we have the pleasure to listen to Halef Yaddaden from the University of Nagoya and about schemes of double shuffle and distribution relations among cyclotopic multiple zeta values. So
Okay,
please.
Thank you for the introduction, and thank you for the organizer for the invitation. I'm really glad to give the talk here in this platform. The talk is about, like you said, about the schemes of the double shuffle relation. So this is a joint work with Henrik Bachmann. Actually, the talk is more is more introductory of double shuffle and distribution on cyclotomic multiple zeta values. So if maybe some of the audience are not familiar with this concept, so it will not be so hard to follow. And then we introduce the new results we have on this perspective with Henrik Bachmann. So we start with double shuffle relations, and first I define what we call multiple polygon values at nth roots of unity. So there are these series of complex numbers where we have the same number of variable of positive integers and nth roots of unity. So the number of variables is called depth, whereas the sum of the ki's here is called weight of the NMPV. And so this series converges when the first and the first integer and first root of unity are not equal to 1 at the same time. And so for this definition, I choose this particular order. So, but maybe in the literature you can find another definition for the summation where the order is backwards. But for my case, this is my favorite order, so I use that. And so these are called cyclotomic also called cyclotomic multiple zeta values. And so the following example is a motivation for this naming. So in particular case, when n is equal to 1, so this cyclotomic multiple zeta values gives what we call multiple zeta values. So in a way, these NMPVs are a cyclotomic generalization of these multiple zeta values. And NMPVs in general can be expressed as so they are expressed as iterated sum, but they can also be expressed as iterated integrals. So using this expression here. So first, by iterated integrals, I mean the following convention where when we have a bunch of differential one forms, we can define iterated integrals inductively like this. So for one form, it's just so the integral of the function, and for the product of one form, so it's so we start with the first, and then we integrate the other forms like this. So I know that sometimes people use the other convention where it's like composition of functions. So I'd like to clarify that this is the convention I'm using here. And in this way, we can express these NMPVs as iterated integrals, where the differential one forms here, so omega 0 and omega indexed by a root of unity are like this. So omega 0 is dt over t, and omega of a root of unity zeta is dt over zeta inverse minus t. And in this expression, what we notice, sorry for the typo here, so it's K2, not I2. So the order of these integers is preserved here with -1. And for the roots of unity, so we apply a successive product each time here. So this is the expression we have here. And as we can notice, if we make a product of NMPVs, they can be expressed as a Q-linear combination of other NMPVs. So basically, it means that if we take the Q vector space generated by NMPVs, this is actually an algebra for the standard product. And to illustrate this, so I use this example here. So in the first case, it's the most basic example one can take. So with Z1, Z2 being roots of unity different from 1, and computing L1 of Z1 and L1 of Z2. And I do this by using the both expression from iterated sums and iterated integrals. So from iterated sums, we obtain this identity by studying the different cases of comparing M1 and M2. So M1 greater than M2, M2 greater than M1, and M1 equal M2, and then we obtain this identity. Whereas for the iterated integral expression, so we use the identity in the bottom. So when we do the product of iterated integrals, we actually do summation of integrals over, this is the NM shuffles. So by NM shuffles, we mean permutation from Sn plus M, which are increasing from 1 to N, and then from N plus 1 to M plus 1. And from this expression, we obtain, for this product, we obtain two different expressions. And by joining these two different expressions here, so we obtain a new relation between these NMPVs. And this is the kind of relation we call double shuffle relation. And so therefore we have this. So this is called double shuffle relation. And then we also have what we call regularization relation. So for regularization relation, we define this by what we say by formal vanishing of divergences. So this is illustrated more formally in, for example, Hoffmann, Ihara-Kaneko-Zagier, Arakawa-Kaneko for n, and Zhao for n greater or equal than 1. But I can give you just a rough example just to illustrate how this regularization works. So basically, regularization means that we kind of pretend that zeta 1 has a meaning, and then we can apply the double shuffle relation we have previously defined. So if we apply the double shuffle relation here, so if we apply the sum relation here, so we obtain the identity on the on the left hand side. And if we apply the if we apply the iterated integral identity, we obtain the identity on the left-hand side. And by joining them, we notice that so the zeta 1, 2 will vanish, and then we obtain a new relation, which we would not have been able to obtain with just classical double shuffle relations. And actually, so for this is the example for multiple zeta values. So for the n equal 1 case, and in this case, it is conjectured that all double shuffle and regularization relation generate all the possible algebraic relation between multiple zeta values. Okay. And then finally, so with this new set of relations, so we have double shuffle and regularization system of relations. And so this is one of the first viewpoint of here, which I like to call it the number theoretic point of view. And there's also another point of view of this relation from the geometry, and more precisely from the motif side. And this is illustrated in this in the following. So we define a series, a generating series of these NMPVs, which phi k, which we denote by phi kzn. So this is this generating series plus some regularized terms from here. So I just wrote this way for simplicity, but these terms can also be kind of other NMPVs obtained in the non-regular case. And so this is called this phi kzn in this context is called a cyclotomic associator, and for n equal 1, it's the Drinfeld associator. So it's a generalization of the Drinfeld associator in the cyclotomic case. And this kind of series satisfies this identity for this delta shuffle. So delta shuffle of phi kzn is phi kzn tensor phi kzn, which we call in the language of Hopf algebra to be group-like. So this phi kzn is group-like for this delta shuffle. And a delta shuffle here is so it's is a coproduct for this series algebra, and is defined by stating that its generators x0 and x zeta are primitive, which means that x0 is sent to x0 tensor 1 plus 1 tensor x0, and x zeta is sent to x zeta tensor 1 plus 1 tensor x zeta. So in this case, the terminology calls this to be primitive. And so the x0 and x zeta here are actually representative of these iterated integrals we have here. So they are non-commutative variables. So we see these differential one forms here as non-commutative variables in this context, and this is the motivation for having this this series in this expression with the language of x0 x zeta. And then to express the double shuffle and regularization relation in this context, so we have this proposition from Racinet's paper, which states that another series called phi kzn star is actually group-like for a coproduct delta star. So delta star is another coproduct, and in this case, so it's defined on a particular set of series algebra. So the coefficient must be x0 k minus 1 x zeta, so written in this form. So it's not like a sub algebra of this series, but so it's not the same. So it's just strictly a sub algebra. And this is coproduct here, and it's defined by the following expression. So in this expression, so we take one generator of this algebra, so x0k minus 1 x zeta, and then we correspond it to so this element tensor 1 plus 1 tensor the element, and plus all the sums that enables this exponent here to obtain this k minus 1. So here, sorry, to obtain k, so L plus k minus L is equal to k, and eta multiplied by zeta eta inverse is equal to zeta. So this is the way we see this coproduct. And as for the series phi kzn star, so it's some sort of twisting. Well, I will define this later in more precise way, but this is somewhat twisting the series phi kzn and then multiplying it by this exponential here, where so this notation here is the x0 n minus 1 x1 coefficient of this phi kzn series. So this is the way we express double shuffle and regularization. And if one wants to check how this is actually expressed, so it's so using this identity, one can check on the coefficients that this identity is exactly what we obtain by a double shuffle and regularization. And actually, so in the following parts, we will explain exactly why this, how exactly this works. Okay, so this first part is like to give the basic idea of this story of double shuffle and regularization, and now we will jump to the formal study. So the two kind of sets of formalisms we have for double shuffle and regularization relations. So we'll study two kind of formalism. So the one from Racinet, so this is the one from the series point of view we saw here, and there's another one from Arakawa-Kaneko, which actually studies it from the first point of view, so from somewhat more like number theoretic side. And actually I call it Arakawa-Kaneko, but it's because it's the general n case. But for the n equal 1 case, so this has already been studied, for example, by Ihara-Kaneko-Zagier and Hoffmann. So and this is the original idea of Hoffmann for defining this kind of formalism. So first, I'll start with the basic integral of this formal study. So here we're in a more general setting. So instead of taking just the group of roots of unity, one can take a finite commutative group of order n. So despite being commutative, I like to denote the product of this group multiplicatively, so to mimic the roots of unity. And instead of taking the algebra C, so we'll take K to be any commutative Q algebra, but not necessarily a field. And we'll denote a set. So this is a set of letters X indexed by the group G and 0. And we will have another set of letters called YG, which is indexed by positive integer. So it's a couple of positive integer and elements of G. And then we define this K model automorphism QG, which is basically, so if we take this element of a basis of K double bracket G, which is the algebra of series over xg. And this QG is defined by actually doing the successive quotient of the root of the elements of the group. So, and letting the other exponent as is. And this is actually the inverse. So this is an automorphism, and its inverse is actually doing the successive product. So the successive product is the phenomena we saw happening in the iterated integral expression of NMPV is kind of function, because this is the one we're going to use later on. And now we start with the Racinet's formalism. So for Racinet's formalism, so the ambient algebra is this one, so K double bracket XG, which is the algebra of series over XG, and XG is the alphabet we defined earlier. And again, I remind that the letters here are non-commutative, so this is a non-commutative algebra. And this is equipped with coproduct, so which makes it a Hopf algebra. And this coproduct is like we defined earlier. So this is the delta shuffle, which makes every element, every letter of this series algebra to be primitive. So defined by this expression. And we can see on the other side, we have the algebra K double bracket YG, which is the algebra of series over YG. So the other set of we took, so where the letters are indexed by a couple. And this is also equipped with Hopf algebra coproduct, which is denoted delta star, or delta Staffel, is also called delta Staffel, and it's defined like this. So the expression is first taking the somewhat a primitive part plus the part here where the sum of variables will give k, sum of integers here will give k, and the product of elements of the group will give g. So just like the delta star we saw earlier. And actually, so without these coproducts, so just as algebras, we can see K double bracket YG as a subalgebra of K double bracket XG. Thanks to this identification, so we will identify it with the subalgebra here of linearly generated by one, and words ending with xg, g being here only an element of the group, so different from 0. And the correspondence, like ykg, is associated to x0k minus 1 and xg. And we can also project, so thanks to this identification, we can also project k double bracket to xg to k double bracket yg by projection pi y, which is naturally defined by the fact that we have a decomposition of k double bracket xg linearly, so just as k submodules. Elements from this algebra, so elements ending here linearly ending with xg, and other element ending with x0. So basically the projection is just for getting all the elements ending with x0 here, and then we obtain this projection. And thanks to this, Racinet defined a scheme, the DMR, which takes any commutative Q algebra K to a set DMR of K, which is a set of series of K double bracket XG. With this notation is for coefficients. So this means that the constant coefficient is equal to 1. The x0 coefficient and the x1 coefficient are both equal to 0, and then we satisfy these conditions. So we have group likeness for the delta shuffle of phi, and we have the group likeness for the delta we have group likeness for the delta shuffle of phi star, and phi star is this exponential, and then the twist is like this. So we first take phi, and then we project by pi y, so we forget all the elements ending with x0, and then we take the successive quotient of all elements of G. So this is the twist we make for the series phi here. And this element is required to be group-like, so that we satisfy here, so the double shuffle and regularization relations here. And in this way, so in this formalism, one can express the classical double shuffle by stating that the series phi kzn is actually an element of DMR of C. And now, so for the second formalism, so this is the Arakawa-Kaneko's formalism. And in this case, so first, the ambient algebra is, this is a polynomial algebra over the alphabet xg. And it is equipped with a product. So this is a shuffle product, which also makes it a commutative algebra. And this shuffle product is defined inductively like this. So this is the shuffle product. So which means, for example, here, this is a letter and this is a word. So U is a letter, W1 is a word, V is a letter, W2 is a word. So I start by shuffling the letter here by taking the first letter and then shuffling the remaining words, and then I add the first letter of the second component, and then I shuffle the remaining words. So this is the shuffle product, and this makes Q of Q bracket xg commutative Q algebra. And on the other side, we also have a commutative polynomial, a non-commutative polynomial Q algebra QYG. Which is an algebra for the Q bracket xg for the concatenating the letters, but is also equipped with an algebra structure for this star product, which is called the Staffel product. And it's defined, this Staffel product is defined as follows. So here, we take first, so then we do the same. So we take the first a letter and then a word and then a letter and a word. So we're starting here by shuffling. So just we did here, but then we add another stuff, which is adding the coefficients here. So I add k1 with k2, and then I do the product of G1 and G2, and then I staffle the remaining words. So this is the staffle product, and this makes of Q bracket YG a commutative Q algebra. And again, so only as algebra for concatenation product, I can see Q bracket YG as a subalgebra of Q bracket XG by the following identification. So it's basically the same as the previous one. So because this QYG is linear algebra generated again by elements here ending with xg, so indexed by the elements of the group, and this enables us to see this as a subalgebra of QXG. And then we have here subalgebra of a subalgebra called H0 index G, which is the subalgebra of we also call it a subalgebra of admissible words, and by admissible we mean that the rule is that we do not start by x1, specifically x1, so with 1 being the identity of the group G, and we do not end by x0. And so this expression here basically conveys this. So which means that we start by if we start by x0, so we end by xg, and if we start by xg, so g must be different by 1, and we do not end by x0, so we are elements of qyg. So the rule is the rule is that we don't start by x1 and we don't end by x0. So that so this is the condition we need to have for in the iterated integral expression, so that it converges. And so for this, so this is an algebra for the standard concatenation product, but it's also an algebra for the shuffle product, and then so Q subalgebra of QXG. And so to illustrate, first we'll illustrate here in this setting how one can express double shuffle regularization relations. So for the double shuffle, so we consider the following example. So we take a linear map from this H0, so the algebra of admissible words, and we send it to C. And so the algebra is we take one here to 1, and for an element here, so for an admissible word here, we take the corresponding NMPV here. So by preserving here the order of the Z1, the R, and so on. And if one makes the harmonic product or the Staffel product, so of y1 z1 and y1 z2, so we obtain this identity here. And if we transpose this to if we transpose this by this map ZC, so by this ZC we obtain this expression of by NMPVs. And here, so if we do ZC of this one, so in order to satisfy the Staffel relation, so the harmonic relation, we need to specify that this ZC must be an algebra morphism for this Staffel product here. And on the other side, if one makes the shuffle product, so for the shuffle product of xz1, xz2, so it's given by this expression here. And again, if we compose by zc, so on the right hand side we obtain this expression, and in order to obtain this left hand side expression we saw earlier, we need to specify that the ZC must be an algebra morphism for the shuffle product. And so this is an example, and in a more general way, so we express this as a scheme. So just like Racinet did, actually we find out that this is expressed. This is so not written in this setting, but actually somewhat written in SP Novellier Racinet. But our motivation to define this is to mimic what Racinet did. So we define a scheme EDSG. So EDS, so it's from the commutative Fourier algebra K to a set EDSG of K. So this is the set of linear maps from H0G to K, such that we have the following conditions. So the first condition is that so Zk is an algebra morphism when H0 is equipped with the shuffle product. Whereas if we want Staffel and regularization relations, so here we need this composition to specify this composition. So this composition here is with rho zk inverse. So rho zk inverse is defined as follows. So if so it's a linear automorphism of k bracket t. So with t just so k bracket t is an algebra of polynomial over t. And we specify it by stating that if we compute the exponential of by this rho of zk, we obtain the product of so we obtain this product here, so this exponential map and then exponential tu. And if one wants the actual expression on k bracket t, again one just have to check on the coefficients. So for example, from this expression we can obtain the coefficient of any the image of any tu power of m over m factorial, for example. So from this expression here. But this is like the most common way, and for the actual way this expression is stated, for example, in Ihara-Kaneko-Zagier's paper, and maybe this is the most common way of using it. And so the QG here is so this is basically the same. This is the same QG from the successive quotient we defined for the series, but here it's defined for polynomials, so it's like a non-bold QG. But basically, this is the exactly same expression. And in the middle, we have this ZK shuffle. So for ZK shuffle, so this is an extension of the map ZK to the algebra QYG equipped with the shuffle product. So this is defined as follows. So we so this is this is identified with ZK when we take elements on H0G and we send X1 to T. Because the main thing with Q bracket YG compared to H0G is that in Q bracket YG we allow words to start with X1. So whereas in H0G we don't allow them to start with X1. So in order to define this algebra morphism, so we need a condition. We need to specify a condition on where one can send X1, and then X1 is sent formally to this variable. So this is from where comes the formal vanishing of the regularization story. And then if one takes this composition, so it will be a map from Q bracket YG to K bracket T. So this is commutative polynomial algebra. And we need to specify that this is an algebra morphism for the Staffel product. So that we satisfy here Staffel regularized relations. So with these conditions, we define this scheme of double shuffle and regularization relations. And now we will explore the relation between the two formalisms. Actually, it's worthy to state that this relation is kind of known by the community in a way that it's like folklore for specialized or multiple zeta values, that one can jump from the series expression and the polynomial expression in a way, but it's not like concretely written anywhere. So this was actually the first motivation for us to work on this direction. It was to write concretely how this formalism actually works. And this is what I will describe here. So this can be done. So in order to do this, so for commodity, so I will denote by L either XG or YG, and then by bullet either the shuffle or the Staffel product. And then I define this pairing. So this pairing is actually it's a bilinear map from the double bracket L tensor product Q L. Sorry, it's a linear map. To K, and I will evaluate it on a word here. So I take a series phi here, and I take a word here, and I take just the W coefficient of phi here. And then I will complete by a linearity for the whole expression. And the actual identity that links between the series and the polynomial universe is actually expressed by this lemma. So this lemma states that we have, in order to express the delta bullet of phi, so the coefficients here will be the coefficients of phi, the u bullet v coefficients of phi, and u tensor v. So this expression relates between this coproduct, so this bullet, the delta bullet coproduct, and this bullet product. So this is worthy to explore a bit the proof of this lemma. And in order to do that, so I will do this only for the case where L is YG and where the bullet is actually the Staffel product. Because for example, in this case, for the shuffle case, this is already proven, for example, in the Rothenauer's book on free algebras. And so he does it differently. So, but our proof here can also be applied for the shuffle case. And actually, in the paper, we did it in a more general notion of a quasi-shuffle product. But for the needs of this talk, so I will only focus on the Staffel product. So first, so this lemma, so this lemma here, the expression here is equivalent to state that if I take the u tensor v coefficient of this delta bullet phi, it will be the phi. It will be the u bullet phi of the u bullet v coefficient of phi. And it will also be by linearity. It will also be equivalent to state that this is the u tensor v coefficient of delta bullet w. So w is just a word instead of a whole series. And so this is equal to the u bullet v coefficient of w. And this will be done by induction on the length of w. So here, so we still write w as, so this is a letter, and w prime is the remaining of the word. And we write u as another letter, u prime, and then the remaining word, and so same for v. And then so we compute this coefficient here. So first we use the fact that this delta star is actually an algebra morphism, and then we use the identity of delta star of y and g. So this enables us to obtain the first equality here. And then we use so here, so in order to obtain this equality, so we use we remark the following. So in this expression, so in order for us to start with in order for us to have a coefficient here, so we need that this ykg and the yk1g1 to be the same. So we need that this starts the same as this one starts. And for the second term, so we need that this one starts the same as this one starts. And also for the other terms, so we need that to have the same starts here. And then we express here by using Kronecker delta and stating that so we have a coefficient here when the ykg is equal to yk1g1, and we don't have any coefficient if this is different. And then so the coefficient in question we will have here in that case will be what remains from this expression, which means that this one and this other one. So this is the only thing that will remain here. And then we apply this exact same principle for the other terms, so which enables us to obtain these identities here. So we're here, of course, because we have two kind of coefficients, so we have the product of the two deltas here. And then, so the third equality will be using the induction hypothesis, because for length, for lower length, so the identity will be assumed to be true, and then we will obtain these expressions. And then we will use, for the final equality, it just remains to use the same machinery we used here to express this in terms of delta, but in the other way around. And then we obtain the equality that this expression is actually the U Staffel W V coefficient of W. So this proves the lemma. And then we will use this lemma, which establishes a relation between coproducts and products for to compare between our two expressions of double shuffle. So first we will need this proposition, and for this proposition we will introduce this notation. So it's capital phi and small phi. So this series is actually defined as a series where the coefficients will be phi of W, so the images by phi, where phi here is so it's a Q-linear map from the commutative from the non-commutative polynomial algebra to K. And this linear map is actually an algebra homomorphism if and only if this series is group-like. And the proof is assuming the lemma, so the proof will be rather simple. In this case, so if one computes the delta bullet of this phi, so it would be from the lemma, so it would be the phi index small phi, the W bullet V coefficient of this capital phi index small phi, and then the W tensor product V. But this coefficient here, so the coefficient of the series by definition is actually phi of W bullet V. And on the other side, if one computes the coproduct, the tensor product of this capital phi index small phi by itself, so from linearity, so we obtain this expression here. And then if, therefore, if one assumes phi to be an algebra homomorphism, so we will have equality of the right-hand sides, which will get us the equality of the left-hand sides, which means that capital phi index small phi is group-like for delta. And on the other side, if one assumes group likeness, so we will obtain equality of coefficients of the series, and the equality of all of these coefficients means that phi is actually an algebra homomorphism. So this establishes the equivalence between these. So so in this vocabulary, so for linear map, we state that we have an algebra homomorphism for the bullet product, and this is equivalent to state that, so this is the delta bullet here, forgot the bullet. This is equivalent to state that this series is actually group-like for the delta bullet. So there's an equivalent vocabulary between being algebra homomorphism and being group-like. And from this observation, so we have this theorem here. And again, so we kind of have somewhat similar setting in Espinovelli Racinet for when n is equal to 1. But here, so we express it in a more general case, and G here will be commutative group rather than just the roots of unity. And in this case, we will state that we have equivalence of for a linear map to be in EDS, and for this series phi indexed by evaluation of 0 and ZK shuffle bar to be in DMRG. So here ZK shuffle bar is actually the extension of the ZK shuffle to the whole algebra Q bracket X. So as a reminder, so we first did the first extension by stating that we send, so we have, because the map is defined on X0, on H0, and then we extend to Q bracket YG by stating that we send X1 to T. And then we can extend to the whole algebra by stating that we send X0 to 0. And so this, so the linear map we take here is is this one. And so phi index, so the notation here, it corresponds exactly to the convention we have here. And so the fact that ZK is in this EDS is equivalent to this DMR to be in this to this here to be in this DMR. And so for the proof, since we have, so if this is an algebra morphism, so this composition here, so from this composition we will have an algebra morphism, and then we can apply the lemma to the propositions to state that phi is group-like. Sorry. And the other case is for the star, and for the star, one only has to prove that the star of this series is actually this series here. So we have a bunch of composition of morphisms, and then this ZK being an algebra morphism is equivalent to this to be an algebra morphism, and from the proposition, this is equivalent to be group-like for the coproduct, for the star coproduct. So which give us the equivalent here. And then from here we have a bijection between EDSGK and DMRGK. Thanks to the fact thanks to this correspondence that sends ZK to this series here. Yeah, and the converse map is actually the one and just take the coefficient. So it takes a linear map, which is defined on the words here, to the coefficients of the series here. So this is this is basically the basic idea one has, that these maps can that this double shuffle relation can be expressed as coefficients of this series. Okay, so now finally for the distribution relations. So I just recall that the number of variables here is called depth, and the sum of these ki's is called weight. And then we have a distribution relation among NMPV, which can be, for example, found in Goncharov's paper, which states that if I take any divisor d of n, and any so we can express, and if I take these roots of unity z1 zr to be some d powers, so we can be written as some power of a root of unity. Therefore, we have this relation here. So it's d exponent of weight minus depth, and then the summation over all the possible so all the possible here components here, which its power d will give zi. And which we can express this again in a more general setting by so here we have a group G of order n, and we take a divisor d of n, and we write this group GD, which is just the d power. So it's the elements of G, which can be expressed as the d powers of any elements here. And so the double shuffle and distribution, actually the regularized ones, are expressed by Racinet in this setting like this. So by stating that we have this identity for this series, so the P star D of phi is actually this exponential here product with the I star D of phi. So this P star D and I star D are defined as follows. So the E star D is actually so I sent x0 to x0 and xg to xg if g is an element of GD, and to 0 otherwise. And for the P star D, so I sent x0 to dx0, and the xg to xg power of d. So here I do the d power, and here I retrieve an element, whereas whenever I have it expressed as d power. And so from there we obtain what we call rigorized distribution relation. So it's distribution relation plus allowing some divergences. And so here we express. So we're going to express this distribution relation in this EDS setting we have introduced. And to do so, we define E sharp D and P sharp D instead of star. So for E sharp is just somewhat of an inclusion map. So I take x0 to x0, and I see an xh as an xh. So here it's in x g power of d, and here it's in sorry, this is xg, and I just see an h as in gd as an h in g, and I just take the same image. So it's some sort of inclusion here. And for the p, I will take all the possible summation. So for x0, I take dx0, and for xh, I will take all possible summation of whatever gives me this h as a d power, since this h is actually a power of d. And then we have this relation using the mapping we already introduced earlier. So this is the somewhat of a duality relation between the star and the sharp version of I, and the same holds for P. And so in this expression, so we see how this the star version is related to the sharp version here. And thanks to this, so we express the how distribution relation will formally work in our EDS setting. So first, just with distribution. So distribution can be expressed with this formula by stating that if I take a linear map and then its composition with P sharp will give me the composition with the I sharp. And in order to see that, we can go back to the previous example we introduced. So this is the ZC. So ZC is the map which take a word here and give us an NMPV. And I choose a divider of n, and I will compute the image of ZC composed with P sharp D, which enables me to obtain this expression here. And on the other side, if I compute ZC, the image of this admissible word by ZC composed with I sharp D, I will obtain this expression here. And then by replacing this ZC by NMPV, so by its image, I will, so the right-hand side of both identities enables me to obtain the usual distribution relation I previously introduced. And in order to express regularized distribution relations, so we will so in this case, so we'll take a series, and then we will assume this identity here. So this is so the ZK shuffle bar is the extension of ZK to the whole algebra K bracket X G. And the sigma here is a series, so it's a K-module automorphism of K bracket T, which is defined in the same fashion as the row we saw for the regularization. So we take its image by an exponential here, and it will be a product of an exponential modulo this coefficient, and then exponential TU. And from this setting holds because we have here that if map is ZK is satisfies extent, so is an element of EDSD, so the previous series here will be an element of DMRD. So which here I will not display the proof, but so this is just computations on coefficients. So we check that the coefficients of this series will actually, so by checking this identity, that the coefficient of this series will give us the identity we had on distributions. And finally, so I will display an application of this setting using EDSD in a way that it enables us to show this conjecture of Zhao. So Zhao conjectured this in his 2010 paper, stating that in weight 2, so all regularized distribution relations are consequences of the extended double shuffle relations, distribution relations of weight 1 and distribution relations of depth 2. So this conjecture is in weight 2, and actually in his paper Zhao states that this holds for up until n equal 169, and I can imagine that he did some computer computations, and then he realized that. So for here I talk about the n for this n, so not the weight. So this is a weight 2 result, but for this n, and so our setting will enable us to show that this holds for any n, not only up until 169. And so there are three things here. So we want to express regularized distribution relations, and for this we need extended double shuffle relation. So extended is just another word for regularized, and distribution relation of weight 1 and distribution relation of depth 2. So this is expression, this conjecture is actually equivalent to this theorem that we have proved. And the theorem states that if we have a Q linear map from X0G, which satisfies the three hypotheses here. So the hypothesis is that ZK is an element of EDSG. So being an element of EDSG means that we satisfy the regularized double shuffle relations, and we satisfy this identity. So the composition by P sharp D is equal to the composition of, by I sharp D of XH. So this is the distribution relation of weight 1. And we also have the third point, which is that composition by X, again by P sharp D and I sharp D of X, H1, X, H2 are equal. And this is a distribution relation of depth 2. So this expression, and this is all thanks to the result we have formulated here. And so to conclude, so this is the hypothesis. And then the result is that we have this identity here, which is satisfied. And the identity expressed here is actually regularized distribution of weight 2. So here, H1 and H2 can both be 0. So contrary to here. So here, H1 and H2 are not equal to 0, but here they are allowed to equal to 0. So this identity holds for any H1 and H2 here. So to conclude this, I will just display how the idea of the proof and how the proof is organized. Actually, there are rather simple cases where this can be checked. So these are case 1, case 2, and case 4. But as for case 4 and case 5, actually we will need this expression of the distribution, and these are the actual two cases where we use the fact that we need a regularized distribution in order to make this expression. So in order to do that, so we express distribution relation of depth 1 here, weight 1, the depth 1 here, and the depth 2 here as elements of H0. And we express also what double shuffle looks like in H0 and regularized double shuffle, and then we obtain this expression for distribution of depth 1. So the expression actually is equal. So if H is equal to 1, So this is an expression obtained by regularized double shuffle and double shuffle relation. And if H is not equal to 1, so this is obtained by double shuffle, regularized double shuffle, and distribution relation of depth 2. So we need all the assumptions. And so these two cases, so case 4 is basically the case where H2, so this is H equal 1, and case 5 is actually the case where H is different. We use this identity where H is different from 1. And this is the only instance where we actually need to use double shuffle and also regularized double shuffle relations. And then for cases 6 and 7, so these cases are actually deduced. So the case 6 is actually deduced from case 4, and case 7 is more twisting of if using some identities on shuffle on the of the shuffle product. So overall, so this basically illustrates how how this works. And thanks to this setting, so we were able to prove this because the actual difficulty of this conjecture, and why I guess Zhao led this as a conjecture, is that from his perspective, so the definition of distribution of regularized distribution he has is actually this one. So this is the one introduced by Racinet. And from this perspective, if he actually wanted to check the identity, maybe he will have to do some sort of huge computations on and evaluating on coefficients to state if identities are true or not. But thanks to this setting, so we actually kind of identified these coefficients, and then we find a way that it is easy to make. So this concludes my talk, and so yeah, sorry for overstepping a little bit, and thank you very much for your attention. So this last slide is the table of contents. So resuming the plan of the talk. So please use it if you have any questions. So, and again, thank you for your attention.
Okay, thank you very much. Are there some questions or remarks? No? Okay, so I would have a question about the last conjecture. So as I understand properly, you have a proof of this conjecture by Zhao. But my question is, why is that conjecture only formulated in weight 2? What is special to weight 2 corresponding to the other weights?
Actually, so in his paper, Zhao tries. He has some formulation of because his overall topic is the study of standard relation among LMPVs, and he has some formulation of study of lower weights, for example, 2, 3, and 4, if I recall. So I guess this is one maybe among among the lower weights, and maybe one of the easiest that he can prove. Actually, maybe he can prove, but he sees as accessible. But actually, for example, this case, I think maybe the motivation is that he wanted to know how much. How, I mean, what is the minimal we will need for some sort of relation. So for example here, so we have regularized distribution, which can express by just the usual distribution plus using regularized double shuffle. So in this weight 2 case, so we kind of can so the information of regularized distribution like not needed. We just need the minimal information we need is just the normal distribution plus a regularized double shuffle. So I guess maybe the motivation is just like this. So, but I don't see this maybe generalized to other weights, but maybe other lower weights, but more general weight. I'm not optimistic in the fact that it can be generalized. But yeah, so
Okay.
I just think that it's the somewhat some sort of like studying these relations and just expressing what happens in lower weights, and then he formulated this because he checks until n equal 169 that this is true. So
Okay. So in other words, starting at weight 3, are there candidates to relations which are different from double shuffle distribution extended?
uh, uh, actually, that I don't really know because
Okay.
so
Okay.
in Zhao's paper he calls it standard relation. All these relations are called standard. So,
Yeah. Okay. Okay.
but
So are there candidates for non-standard relations?
uh, I mean, it's hard to tell,
Okay. It's
because,
hard to
for
tell.
example,
Yeah.
multiple
Okay.
polylogs, we can have some, I mean, some unusual relation, but it's like very particular cases, and
Okay.
somehow seems like some coincidences of relation happening.
Okay.
Mm.
Okay. So
And
that's
yeah, because
yeah.
actually there's
Yeah.
no like unlike, for example, for multiple zeta values, there's no here like a conjecture stating that all we
Hmm.
need to express all algebraic relation are just double shuffle regularization and distribution and maybe regularized distribution. So we don't have like such relations.
Okay.
I mean
Just
such conjecture. But
okay.
the conjecture only is formulated for multiple zeta values, and so we
Hmm.
have strong reasons to think that it's true. So.
Okay. Okay. Thank you. Are there other questions? So if not, we thank Halef again.